All right, so I'm pleased to introduce Michael Sinatra from ESnet, and he is going to be giving hopefully the first of a couple of part talk on cryptography. He gave this to ESnet staff a couple of months ago, and I thought it was great, and it would be a good topic for everybody here. So I'll turn it over to Michael.
Okay, thanks, Jason. I'm assuming everyone can hear me pretty well. So let me get into this talk and talk a little bit about what I'm trying to do here. A couple of things. When I was working with some ESnet staff, I was trying to get some more people interested and sort of up on the latest in DNS, and in particular DNSSEC. And I realized that to understand some of the concepts of DNSSEC and even some of the basic concepts of DNS, it made some sense to understand cryptography. And it was useful to provide sort of a foundational knowledge to folks in sort of the basic concepts of cryptography. We're not going to get too much into math or anything like that. We're just going to go through some of the concepts and sort of really try to understand what are the uses and limitations of cryptography, where do the vulnerabilities occur, how do we mitigate those vulnerabilities, and how does that influence our choices of which kinds of cryptographic algorithms to use, what kind of key lengths to use in the various applications that we put them to. And I think that there's sort of a general use for this kind of topic, both in providing foundational knowledge to both networking and systems engineers, and also people who are doing cyber infrastructure type stuff, people who are doing data transfers to make sure that the integrity of the data stays the way it's supposed to be as it's transferred across long distances, and also things like data provenance, where you want to make sure that the data is not intentionally messed with in some way or forged, or some type of scientific fraud isn't going on. So it's important to do this in the field of scientific computing and cyber infrastructure, and it's also, I think, important in a lot of different things that we do today, as cryptography, encryption, the need for those sorts of things, privacy and integrity and authenticity are becoming more important to us in general. So you can see the order of stuff I'm going to talk about here. It's fairly simple. I start off with the building blocks. I start putting together and trying to create different types of security protocols. And then I talk about how we manage trust across the internet and across, sort of our daily lives when it comes to the use of information technology. I'm going to use words like plaintext and ciphertext quite a bit. They're common terms in cryptography. Plaintext refers to the stuff that's not encrypted, and ciphertext refers to the stuff that is encrypted, quite simply. Even if it's not actually text, it might be data of some sort. It might be binary data. It might be videos or pictures. So it's still going to be called plaintext because that's the convention that we use. In addition, I will talk about RSA quite a bit, but I am talking about the algorithm that was invented by Rybest, Shamir, and Edelman, not necessarily the company they founded, which provides multi-factor authentication tokens and things like that. So for that reason, it does get people, particularly in the government, very confused, because they use RSA tokens and they're wondering, when I keep talking about this is what RSA does, this is what RSA does, they think about the company and they think about the tokens, not the public key algorithm that they named after themselves. So just keep that in mind when you hear me talk about RSA. So let's start off with some of the building blocks. The most common or sort of simplest and frequently used building block is the one-way hash. And of course, there are cryptographic hashes and non-cryptographic hashes. Cryptographic hashes are one-way functions that are cryptographically secure in that they provide a unique hash. It's very unique to the plaintext being hashed. It's deterministic, and it can't be reversed. In cryptography, there's sort of unfeasible, really, really hard, or impossible. And theoretically, one-way hashes are impossible to reverse. They're not designed to be reversed. They are completely a one-way mechanism. But there are brute force mechanisms and certain types of brute force optimizations that can be used that can allow you to effectively reverse a hash. So that's important to keep in mind. So when we talk about the hash function, it's going to take plain text and it's going to produce a message digest. I'll show you an example of that in a second. There are several different types of hash functions, and this is where we start to get into the alphabet soup of cryptography. Basically, as we talk about vulnerabilities and things like hash collisions, the two on the bottom, SHA-2 and SHA-3, the various algorithms of SHA-2 and SHA-3 are the ones that are still considered to be secure. The ones up top, like MD5 and SHA-1, are now considered to be insecure, and I'll explain why that is right now. There are two ways that hashes are vulnerable. One way is that they can be vulnerable to brute force attacks and to brute force optimizations. One of the ways that you help prevent against brute force optimizations, and the kinds of optimizations that I'm thinking about are things like rainbow tables and things like that, is to use salt. And salt is just simply a random string that is prepended to the hash that is hashed in with whatever the plain text is that you're trying to hash. So in password files, salts are commonly used in the password hashes because the passwords themselves are relatively small. Even if you have a relatively strong password, it might be only 16 or 20 characters. And so it makes it a little bit harder, I should say, or much harder to do things like rainbow tables and other mechanisms. Rainbow table is kind of a complicated concept, but it's a way of basically producing sets of plain text and hashes that you can use as a quick cross-reference if you want to try to do some sort of brute force attack on a set of passwords. If you use a salt, it makes it very infeasible to try to use a rainbow table for hashes because the salt is unique to each password. So even if you make the salt available, even if it's not secret, it actually helps to make hashes much harder to crack using rainbow tables. But that's all well and good. The thing that tends to get a little bit more press in these days because of the way we use hashes in digital signatures and other mechanisms is hash collisions. And hash collision is a big vulnerability for some of the older hashes like MD5 and SHA-1. What a hash collision is basically I can take two different types of plain text and the hash algorithm produces the same hash. That's obviously highly problematic because in order for a hash to be cryptographically secure, it has to be unique. So it's not very easy to achieve hash collisions in situations like DNSSEC where you're just hashing a very small string. But if you're hashing something like a document in order to do a digital signature, or you're hashing a large data set, it's possible to fake multiple pieces of data and do it in such a way that you can get the hash to produce the same output, the same message digest. So for things like MD5 and SHA-1, using them to hash large data sets, if you want them to be cryptographically secure, is not a great idea. It would be useful to move away from those kinds of hashes if you're interested in trying to hash large data sets. If you're just interested in doing things like, I want to check a small chunk of data, then it might still be useful to have MD5 or SHA-1 as your checksumming mechanism, just to prevent bits from getting flipped. But if you're trying to prevent deliberate fraud from happening in a large data set, you need to use a more secure hash, like one of the SHA-2 algorithms or one of the SHA-3 algorithms. So here's an example of using SHA-256. This is actually more properly called SHA-256. It uses the SHA-2 algorithm with a 256-bit hash. And I'm just doing this on my Mac laptop, the laptop that I'm actually using to give this presentation right now. I can run hashes on that laptop with software that's already built in. Using the OpenSSL software, I just tell it I want a digest of some text. Then I enter in the text in standard input and then hit Control-D, and it produces a hash, and you can see the hash that it produces. That hash is a binary blob of data that is represented in hexadecimal. You can see that I did another hash, and I just changed a few things about the text string, and you can see that the hash is completely different. So if you look at it in hex, the hex digits are all different. It's not just a couple of digits changed, it's the entire hash changes. So that gives you an idea of how hashes work and the fact that even if I change a little bit of data, I get a completely different hash. And when I say hash, I'm actually referring to message digest there. I sometimes refer to the output as a hash itself. Again, these hashes are represented in hexadecimal. Sometimes digests or digital signatures will be represented in base 64 instead of base 16 because it's more efficient. Base 64 takes binary data and converts it into an ASCII format that we can actually read, but it looks like random data to us. But what that is you basically take the entire alphabet, uppercase and lowercase. That gives you 52 unique characters, and then you add, 62 unique characters. And then, that is 52. Then you take 0 through 9, that gives you 62 unique characters, and then you add a couple extra characters like the plus and the slash, and that gives you 64 unique values, and that's how you can encode things in base 64. So we'll see base 64 a lot when we look at digital signatures a little bit later on. So that's it for hashes for now. The next big building block that we need to look at is symmetric ciphers. Symmetric ciphers will encrypt and decrypt data using a symmetric key or a shared key. Now you might think, okay, we don't use shared keys that often, so do we use symmetric ciphers? And it actually turns out that we do. We use symmetric ciphers almost all the time when we're doing encryption. And I'll explain how that works a little bit later on. But again, the point of a shared key is you're using the same key to encrypt and decrypt the data. So that means that you have to do key management. You have to exchange the key out of band. But the advantage is that you have very fast and very strong symmetric ciphers because you don't need very long key lengths. You only need 128 or 256 bits of key length to get really good encryption. So one way we can actually do a symmetric encryption is to simply use an exclusive OR, a binary exclusive OR. I point this out, I point out what an exclusive OR is because it's used a lot. I mean, if you program, you probably use exclusive OR quite a bit. If you do network programming and you're trying to find out, for example, you're writing a script that tries to figure out if a particular IP address exists within a particular prefix that's in your route table, you can use a bitwise exclusive OR, binary exclusive OR, to see if the bits match in the between the routing table and your prefix. So you can actually use that to match a route in your prefix table. Now that might not be a very efficient way to do it, but it does work. So it's something that's very handy in a lot of places. Actually turns out that exclusive OR is very handy in cryptography as well. And the way exclusive OR works, very simple on a binary bit of data, is that if I have a 1 and 0 combination, that means that the exclusive OR is true, so I put a 1 there. So that in this case, the quote-unquote ciphertext, it has a bit of 1. If the bits are the same, though, that gets a 0 bit. So I put a 0 here because 0 and 0 are the same. I also put a 0 here because 1 and 1 are the same. 1 and 0 are different, so I put a 1, and 0 and 1 are different, so I put a 1. So you can see now I've created some ciphertext that is completely different from the plain text that I've done. And this actually does work. You know, you can actually encrypt something pretty easily just using exclusive OR. The problem is that, well, the good thing about it is that it can be reversed. If you look over here at my ciphertext, I can reverse it by reversing it against the key. 1 and 0 is 1, 0 and 0 is 0, 0 and 1 is 1, 1 and 0 is 1, etc., etc. You can see how I can reverse it. But the problem is I can also do the same thing for the key. I can take the ciphertext and the plain text and I can derive the key from that. So here you can see that 1 and 1 is 0, 0 and 0 is 0, 1 and 0 is 1, 1 and 1 is 0. You can see how I'm taking the plain text and ciphertext and I'm essentially deriving the key by running the exclusive OR against the plain text and the ciphertext directly. This is a very, very simplistic example of differential cryptanalysis. Differential cryptanalysis is a way in which you can try to break a symmetric cipher by looking at plain text and ciphertext. Now, if you don't have access to the plain text, that's great. Then you can't do differential cryptanalysis. But not having access to the plain text is not something you can always rely on. It's kind of like security through obscurity. It can work in certain circumstances, but it doesn't work in all circumstances. So it's important that we use more sophisticated mechanisms in order to do encryption. But it turns out that we actually use XOR as a building block of a lot of those mechanisms. Another example of differential cryptanalysis is when you do the cryptoquip in the newspaper. What you're being asked to do is you get a little bit of a clue that gives you a little bit of plain text and a little bit of ciphertext. And because we also know the structure of the English language, we can look at the way that the words come out and try to see if maybe we understand a little bit about how the sentence is structured here. And we can actually solve our cryptoquip in the same way that people do differential cryptanalysis, although a much, much simpler way, but a similar way nonetheless. So symmetric ciphers sort of fall into two major types. The most common one is the block cipher. It takes a fixed block of data, usually 128 bits or sometimes 64 bits, usually not more than 128 bits, and it encrypts each block at a time. There's also stream ciphers. The stream cipher actually effectively encrypts data on the fly. So as the data is being fed in, it actually gets encrypted in a stream. And that's the common stream ciphers are RC4 and RC5. A new one that was created by Dan Bernstein and Tanya Long is called Cha-Cha. And Cha-Cha is now becoming very commonly used in SSH, and it is being standardized now as one of the possible ciphers in TLS version 1.3, which is just being implemented. I'll talk about that a little bit later on, how we put some of these together in security protocols. A very common block cipher is DES, although DES is now, because of its short key length, is not very secure anymore. It's no longer considered secure. So it's been replaced by AES, the Advanced Encryption Standard, and that uses 128-bit or 256 bits of key length. Another common one is Blowfish, and that has been replaced more recently by 2Fish and 3Fish. That's Bruce Schneier and a bunch of other people who worked on that. And there's another one called Serpent, which is actually a very strong cipher, but it's not used very commonly. So if you take a block cipher and you want to sort of effectively turn it into a stream cipher, you've got a long string of data that's bigger than 128 bits. How do you encrypt that? Since the block is only 128 bits, one easy way to do it is just to simply chain the data together and encrypt 128-bit blocks and then just chain the output, the ciphertext, into a file, and there you go. This basic method is called electronic codebook. There's a big problem with the electronic codebook, which is if you look at the image, if you've got data that forms a particular pattern, in this case we've got an image, and you encrypt it, in this case we're encrypting it using AES, and you can see that the pattern still shows up. One of the goals of encryption is to make data look like it's random. Encrypted, the ciphertext should look like it's random data. So in that case where we have a pattern, you can see the pattern still comes through. So one way to solve this is to basically bring back our friend XOR. So we're going to XOR the essentially data against the ciphertext for each block that we do. For the first block, since we don't have any ciphertext, we're going to create an initialization vector, which is just a random string. It doesn't have to be secret. So we take that initialization vector, we XOR it against the plain text, we run it through our cipher encryption mechanism, and then we produce ciphertext. We save that ciphertext in our file, or print it out to standard output, or whatever we're doing with it. We save it, put it wherever we're going. And then we take that ciphertext from the first block of plain text, and we XOR it against the second block of plain text. So the first ciphertext block gets XORed against the second block of plain text. That gets then run through your encryption algorithm, and you produce a second block of ciphertext, which you then save and XOR against the third block of plain text, and so on and so forth. This method is called cipher block chaining, or CBC. CBC is a very common, because it's very simple and very easy to implement, mode of operation. It's a very simple and common and fairly secure way of producing effectively a stream of ciphertext from a stream of plain text. There is one big problem with CBC, though, which is that it is now becoming more susceptible to attacks that use differential cryptanalysis. That's usually not that big of a problem, again, where you don't have the plain text, but even in protocols like SSH or TLS, where the initial handshake of the protocol can be predicted. In other words, if I understand how the protocol works, I can, in my head, understand what some of the plain text is going to be at the start of the protocol. If I have the first few blocks of ciphertext and I kind of know what the plain text is going to look like, I could potentially do differential cryptanalysis against a blob of data that is encrypted with some encryption algorithm and CBC. So it turns out that's one of the reasons why, for example, SSH no longer recommends the use of CBC as a mode of operation. A common mode of operation that they recommend is either GCM, which you can see is in that list down below, or they use Cha-Cha as a stream cipher. So a very common use of encryption algorithm and mode of operation is AES GCM. We use the AES block cipher with GCM, which is a pretty sophisticated counter mode of operation. And counter mode is really good because it doesn't allow you to do differential cryptanalysis, but certain types of counter mode like CCM and GCM also provide message authentication for each block that it actually encrypts. That's actually really helpful when we start to talk about message authentication code or MACs, which we'll talk about a little bit later on. But basically, to suffice it to say, AES GCM is a mechanism for producing authenticated encryption. You actually are not only encrypting the data, but you know that the data is the integrity of the data has been preserved. So symmetric ciphers are great. They're secure. They're fast. You can use a fairly small key length, 128 or 256 bits, and you can get really good encryption out of that. But you have to share a private key first. You have to use a shared key, and because you use a shared key, you have to basically deal with key management. Keys have to be transmitted out of band. So how do we do that when we're doing things like going to a website, and we want to encrypt the stuff that's on the website? Or how do we do that key management when we're just trying to send somebody an email that we want to encrypt? So it turns out one way to do this is to use what we call either asymmetric cryptography or public key cryptography. And public key cryptography revolves around trying to find mathematical functions which are really easy to do in one direction and really, really hard, not impossible, but really, really hard to do in the reverse direction. These are called trapdoor functions. In other words, it's easy to fall through a trapdoor, but it's hard to climb out of it. So these trapdoor functions are very commonly used for public key cryptography. One very simple one that's used is, I shouldn't say it's very simple, but it's a rather simple mathematical function that allows you to do this kind of asymmetric key encryption. And it's basically take two large prime numbers and multiply them together. Okay, it's very easy actually to multiply two large prime numbers together. But it's really, really hard to look at a large number and to try to determine if you can factor that large number. It's especially true if the large number is its only result is it's the result of two large prime numbers. If that's the case, then only one of those prime numbers divides it to get the other. So if you need to factor it, you're only going to find two factors and they're large prime numbers. It turns out it's really, really hard to do that. And I give you a very simple example here. It's really easy to multiply 19 by 67. You can probably do that in your head or on paper in about 10 or 15 seconds. But it's a lot harder to figure out what numbers I had to multiply together to get 901. And actually, if you want the answer to that question, I've forgotten. So we'll have to do our own factoring of that. It just takes a lot longer to factor, though, than it does to multiply numbers together. It turns out this is the basis behind the RSA public key algorithm. If you can do that kind of multiplication of large prime numbers, then you can do RSA. There are other types of trapdoor functions. One is called the discrete logarithm problem, and this is simply where you basically try to solve for a logarithm over a group of a finite field. It's one of those things that's hard. It's sort of like you're trying to find, G equals n to the k, and you solve for k. Basically, you're solving for that logarithm. And the third mechanism that's gotten very popular is elliptic curve cryptography, which is not only a little bit of a tongue twister for me, but it's also really interesting and also a little bit hard to understand. But there's a great article on it in the Cloudflare blog, which apparently is also a tongue twister for me. A guy named Nick Sullivan does really great work in explaining cryptography, and his blogs are really, really informative and helpful. And so he explains very well on how elliptic curve cryptography actually works. I'm not going to go into it too much. But just to remember what we're trying to do, the important thing is in key management or in asymmetric public key cryptography is if I encrypt something with the public key, it can only be decrypted with the private key. I can't decrypt it with the public key. And if I encrypt something with the private key, it can only be decrypted with the public key. It can't be decrypted with the private key. Okay, that's the important part of asymmetric cryptography, is that those two principles hold true. So if I want to encrypt something and send it to Jim Warner, I would use his public key to encrypt the data, and he would use his private key to decrypt it. Now, if Jim were to use his private key to encrypt data and send it to me, I would have to use his public key to decrypt it. That doesn't make much sense from a perspective of if Jim wants to keep the data confidential, encrypting it with his private key isn't particularly useful, but it is very useful if he can encrypt it with his private key as a way of telling me that he was the one who encrypted the data. And that turns out to be very useful when we get to digital signatures a little bit later on. So back to alphabet soup, what are some of the algorithms we use in public key cryptography? RSA I've already mentioned. I mentioned DSA as well, the digital signature algorithm, which uses, again, the discrete logarithm problem as its basis of trapdoor function. A similar mechanism is used by Diffie-Hellman. That's only mainly used for key exchange. And I'll talk about how key exchange works a little bit later on when we start putting these building blocks together. There's also something called GOST. GOST is actually the Russian equivalent of NIST. So they have a bunch of standards that are named GOST, and then a bunch of numbers that reflect the year and the mechanism, the particular standard that they were trying to ratify at that point. But in the case of cryptography, there's an elliptic curve algorithm that GOST has standardized, and so that is sometimes used in DNSSEC signatures, as an example. It's actually pretty rare. It's only used by the Russians because they don't like using RSA. And at the time, RSA and GOST were the only mechanisms that could be used. RSA and DSA actually were usable for DNSSEC, but nobody was using DSA, or very few people were using DSA at the time. So it was really RSA and DSA were the only ones that were being used, and the Russians didn't trust those, so they wanted to create their own, and they created GOST. That was one of the ones that they used, and so that's sometimes used in DNSSEC, but it's not used too many other places. Elliptic curve cryptography is also used in a mechanism similar to DSA, and it's also used in an elliptic curve version of Diffie-Hellman as well for key exchange. There are more recent algorithms called ED25519 and ED448. Those numbers represent the particular types of elliptic curves they use, and they use a slightly different algorithm to do digital signing and to do things like key exchange. They use the Edwards algorithm. That's what the ED stands for. And the difference between the Edwards algorithm and standard DSA, I'm going to talk about in, I think, a little bit later on, but there's actually a rather significant difference, which I'll explain in a little bit. Okay. So actually, I explain it right now, what the limitation is there. I talk about some of the practical uses of some of the cryptographic algorithms in public key cryptography. RSA is still great. It's still really good. It just requires really long key lengths. 4096-bit RSA is pretty much now the de facto standard. And that is used in order to protect data and signatures from the eventual, to make it a little harder to use quantum computers to try to crack or factor RSA keys. So you need to have a 4096-bit key to prevent a quantum computer, which for the most part hasn't been invented yet, from being able to crack your keys. There is a group at the NSA called the Information Assurance Division, or Information Assurance Directorate, or IAD. They're sort of trying to downplay their affiliation with NSA, and they're semi-autonomous. But the thing to remember is that what IAD does is actually try to come up with really good cryptographic algorithms, whereas other parts of the NSA, like SIGINT, we think are probably trying to break those same algorithms. So it's kind of interesting how these work. But the IAD recommends certain types of key lengths and certain types of algorithms, and they publish those periodically, and it's a very useful reference to go to. I think I include it at the end of the slides. It used to be called Suite B, and it's now called, I think, Commercial Public Key Algorithms or something like that. It's actually a very useful reference, but they're now recommending at least 3072-bit key lengths for RSA, and I think that 4096-bit is what everyone is sort of settling on at this point. When you get to DSA and ECDSA, the important thing to remember there is that when you sign something using DSA or ECDSA, you need a really good source of random numbers. The signature process requires random numbers to generate signatures. And if I can predict the random numbers that you're using for your signatures, I can actually derive the original DSA key that you used to sign those. So that's actually a very serious security issue. If you don't have good random number generation, using DSA or ECDSA can be problematic. One of the things that people kind of lost sight of, several years ago, there was a vulnerability in the Debian Linux distributions version of OpenSSL. They had basically changed OpenSSL to pick a set of random numbers in OpenSSL's own random number generator that were within about either a 16,000 or about a 65,000 set of numbers. There were only 65,000 random numbers that they were choosing from, which meant it's really easy to brute force that with a computer. That made RSA keys that were generated by this particular library extremely weak. It also made DSA keys weak as well. But what people didn't realize is it also made any DSA signature that was generated by that OpenSSL library incredibly weak, not just because the signature was weak, but because the signature could be used to derive the original key. So it basically created an insecurity in the original key just because the signature was generated using this OpenSSL library. That, of course, got fixed pretty quickly, and a lot of people redid their RSA and DSA keys that were generated at the time that they were using that particular version of Debian's distribution of OpenSSL, but they didn't regenerate the keys that were signed at the time or that used to generate signatures at the same time that that OpenSSL library was being used. So there's still some DSA keys that might be out there that are extremely vulnerable, and people don't realize that. So that's just a practical example of what goes wrong when you require very strong random number generation, and you can't always guarantee strong random number generation. In addition, certain types of embedded devices don't have great random number generators. Increasingly, processors like the ARM processor and Intel processors have a random number generator built in. That is a mixed blessing, but because certain government agencies from certain governments were believed to have been involved in the development of those random number generators, it's not clear if they are good or bad. Depends on what part of the NSA helped create those random number generators, whether it was IAD or whether it was SIGINT. So a lot of people have a lot of suspicions, and I think in some cases the suspicions are a little bit overblown, but a lot of people do have a lot of suspicions about certain types of three-letter agencies and what they did. And since we've got someone from NSF on here, I want to point out that NSF did not do any of these things. It's NSA. So it's important I get my algorithms right, or my three-letter acronyms right, that is. So one of the advantages, by the way, of EDDSA is that it doesn't require that random number generation for each signature that's generated. It uses a different method to generate a large number that can be securely applied to the signature and doesn't actually require the strong random number generation. So EDDSA is now being ratified for use in DNSSEC. The RFCs have just come out, and the latest versions of Bind 912, for example, uses that or can be made to use that algorithm. A number of, I think that TLS version 1.3 is going to use EDDSA for the signature portion, but I'm not sure. I need to look at that again. I think it does, but I'm not positive about that. Okay. Anyway, back to our private and public key methods. I already mentioned this, that the private key can encrypt data that can only be decrypted by the public key, and vice versa. You can't ever use asymmetric keys as symmetric keys, at least not using the asymmetric algorithm. If you just threw an asymmetric key into a symmetric cipher, sure, you could do that. But in this case, if you're actually using the asymmetric algorithm, it has to be the private key encrypts, the public key decrypts, or the public key encrypts and the private key decrypts. Okay, so let's start putting these building blocks together and actually create some security protocols. In a lot of cases, hashes, symmetric ciphers, and public key ciphers are not that useful unless we actually combine them in different ways. And it turns out they're sort of useful, but they'd be more useful if we combine them. And what most security protocols do is combine at least two or all three of the methods that we have mentioned previously in this presentation. So, as an example, public key cryptography. You can actually encrypt a huge blob of data just using public key cryptography. I could take Jim's public key and encrypt an entire 4 gigs of data and send it to him. The problem is it's very slow and inefficient to do that. It actually turns out it's much easier to use the public key to encrypt a session key and then use that session key to encrypt a whole blob of data. Then when Jim decrypts it, he uses his private key to decrypt the session key, and then the session key he uses using a regular symmetric cipher to decrypt the whole blob of data. This is exactly how PGP works. PGP basically works by taking a public key and encrypting it with encrypting a private key or encrypting a symmetric key, and then using a symmetric cipher to encrypt the entire blob of data. And that includes even if you're just sending a short email, it still works that way. The other major use of combinations of things is in digital signatures. And digital signatures use hash algorithms plus symmetric key algorithms. Plus asymmetric key algorithms. So they use hash algorithms plus asymmetric key algorithms. A very common type of digital signature is RSA SHA-1. Basically what you do is you take a SHA-1 hash of a message, you take that digest, that message digest, and you encrypt it with your private key. Then if I want to validate the signature, I decrypt it with your public key, and I run the same hash algorithm on the message data and see if the two hashes match, the two message digests match, now that I've decrypted the message digest. That's the basic way a hash function works, digital signature function works. There are other bits and pieces that go into making it more secure. They also go into making it a little bit more complicated. But it's very common to see hash functions and public key functions combined like this. And so I guess, like I said, RSA SHA-1 is very common. DSA doesn't normally get combined with other hash functions because it always uses the same one. It always uses SHA-1. It's possible to use DSA with RIPE-MD 160, DSA can use any 160-bit hash mechanism. But because 160-bit hash mechanisms are starting to become vulnerable to collisions, DSA is now itself, just regular plain old DSA, non-elliptic DSA, is now itself considered insecure. So that's basically how digital signatures and how things like PGP work. You may also find in something like SSL, you use all three. You have a certificate, a digital certificate. That digital certificate is signed using a digital signature, which combines the hash mechanism and the asymmetric key cryptography mechanism. And then it is used to set up that the data in that certificate is used to set up using maybe some sort of key exchange protocol like Diffie-Hellman or ECDH. It's used to set up a symmetric cipher, which you can then use to encrypt a bunch of data as you are sending data to and from, in some cases, a website, or in some cases, something else that would be secured with TLS. So TLS combines a whole bunch of these methods that we use and creates a larger security protocol. Another common protocol that we use, another common security protocol, it's actually both a building block and it uses building blocks, is called MACs, or message authentication codes. And basically what you do is you take a hash with a shared key that provides message integrity and authenticity. A very simple MAC is just to take a basic hash like MD5, take a shared key, concatenate it with the message, and the hash that you've revealed is valid if I can take the same shared key, because it's shared, I've got the same key, and take the message and run the same hash over it and get the same message digest. With certain types of hash functions, it turns out that this is susceptible to something called a length extension attack. I can actually append data onto the message and produce a hash, even if I don't know, produce a valid hash, even if I don't know the shared key. I won't go into this, but length extension attacks do exist, and they are possible for algorithms like MD5, SHA-1, and even SHA-2, which are still considered to be secure in other respects. So the solution to this is to use a more sophisticated algorithm, and HMAC is very common. HMAC is relatively simple. It involves taking the keys and XORing them, and then hashing them once, and then hashing the message and the hash key again. That prevents basically the length extension attack. So if you combine HMACs with encryption, like what IPsec does, it uses both encrypted payload, or ESP, and it uses something called AH, or authentication header. Authentication header portion is typically an HMAC of some sort. So one mechanism that uses MD5 in a really simple hashing mechanism, a really simple MAC mechanism, is TCP-MD5. That's commonly used to secure not the BGP data that's sent, but BGP sessions, especially when you're on a shared exchange fabric or public fabric. TCP-MD5 is really simplistic. It's probably not susceptible to length extension attacks because of the way the TCP packet is formatted and the way that the checksum works. There's probably enough other things in the packet that prevent this length extension attack from happening. But MD5 is still susceptible to collisions pretty easily. So MD5 has been largely deprecated for a lot of uses. TCP-MD5 is still used. It still does raise the bar for security in making sure that the integrity of a BGP session stays in place. The session can't easily be killed by somebody and create a denial of service attack by that mechanism. But there is a newer standard called TCP-AO, or authentication option, and that allows the use of more sophisticated MAC mechanisms like HMACs and other types of MACs. And I already mentioned that symmetric cipher modes like CCM and GCM provide their own MAC mechanism built in. So the final topic, and I want to leave some time for questions, is if I'm encrypting data like, let's say I want to send data to Jim again. And the only reason I'm picking on Jim is because his video is available, so I can actually see him on my screen. Even if I'm encrypting data to Jim, I want to use his public key to send him a blob of data. How do I know that it's actually Jim's key? So this is a mechanism that is important for not just sending data to a person, making sure you know that it's that person. It's also important for validating digital signatures. How do I know that somebody who claims to have used a digital signature, that really is their private key that they use, or that really is the public key that corresponds to their private key that they use to make that signature? So security protocols, it turns out, really need to have some sort of mechanism of trust. I already mentioned one of them in TLS, because we use the various methods of cryptography in order to create a digital signature, a digital certificate, which includes a digital signature. The certificate mechanism is a way of providing trust as long as there is a certification authority that we trust. So the idea is that the certification authority lends its digital signature to a certificate, and because I trust the CA, I trust the certificate. Now, why do I trust the CA? Well, that's actually kind of a tricky question. It turns out the reason I trust the CA is because I get a bundle of certificates from trusted CAs, or from a trusted source that includes a bunch of CAs that that source trusts. So it's essentially a cartel. So if you notice in your browser, there's a list of trusted CAs in your web browser. There are packages that get sent with Linux distributions and BSD distributions and other Unix distributions that have a list of CAs and include their public keys, their certificates with the public key in them. So in order to do that trust mechanism with a digital certificate using TLS, I basically need to have a cartel, a group of people that are trusted by the browsers, by the various Unix and Linux distributions, which basically says, here's a group of CAs and we trust them, therefore you should trust them. That doesn't always work very well. There are some CAs, like Symmetric, I believe, was the one that gave out a certificate to example.com. There have been a lot, to somebody claiming to be example.com, I should say. There are other instances where some of the CAs have been problematic, and in fact, some of the CAs have actually been kicked out of the browser trust lists, so they are no longer effectively in the cartel. Another method of doing trust mechanisms is hierarchical, which is where you have one trusted entity and it has one key, and everybody trusts that key. And that's how DNSSEC works. ICANN and IANA have created the root DNSSEC key, and that private key is secured in a variety of very interesting and careful ways. And the public key is made available to people via websites and other out-of-band mechanisms. It is also hard-coded into a bunch of DNS server software distributions so that people can use the trust mechanism as a trust anchor, that RSA, that root key as a trust anchor, in order to trust everything that goes down from there. The root key signs all of the keys, or basically signs digests for all of the keys that sit under the root. So for example, in .NET, root has signed the digest of the key that's in .NET. I can validate that signature and validate that digest and use the key for .NET, which then signs the key for ES.NET. And then I can use that to validate the key for ES.NET, and then use that key to validate the signatures that are actually in the ESnet DNS zone. So that I call hierarchical. And another one is anarchical, which simply means the opposite of hierarchical. And that's how PGP works. PGP creates a web of trust that's based on individual people who decide to trust each other's keys and sign each other's keys. And basically the way it works is, if I trust someone who signs Jim's key and Jim signs someone else's key, then I can basically use that transitive trust to say, okay, I'm pretty sure that this person's key is really theirs, especially if it's signed by a whole bunch of people that I trust. Then I can say, okay, here's somebody else's key. Let's say it's Kevin Thompson's key, and I want to send Kevin Thompson a message about some super secret NSF thing, so I want to send him an encrypted message. If Jim and Ulu and Jason and a bunch of other people that I trust have also signed Kevin Thompson's key, a public key, then I might decide that I now trust Kevin's public key. The way people often sign their public keys to begin with is actually to have a PGP signing party, which is where you get together, you exchange IDs like passports, like very strong picture identification mechanisms, and you exchange your key fingerprints. You validate the key fingerprint manually, and then you sign that key with your own key. So that's sort of how anarchic trust works, and it actually works fairly well. But there's still a lot of things about PGP that are kind of cumbersome, and that's one of the things we sort of get to as we get more into security protocols. So I'm going to end it there and basically take questions at this point. I'm kind of interested in sort of the usability of various types of cryptography and some of the failure modes that we get in cryptography as well. You know, PGP is interesting. You know, is it easy to use? Is it hard to use? There's a lot of debate on that. There's a lot of debate on whether DNSSEC just simply increases complexity, increases failure modes, or whether it really helps against a set of fairly strong vulnerabilities, or whether it enables a whole set of cryptographic use cases, like things like DANE and stuff like that, where you can actually create a certification authority using your own DNS server. So I think that there's a lot of interesting ways in which, you know, we can talk about the usability of cryptography. We can talk about vulnerabilities. One of the things I do want to point out, just in conclusion, is that oftentimes when there are vulnerabilities in quote-unquote encryption, we think the NSA may have cracked encryption, or we think they may have cracked certain parts of encryption. It's really actually the security protocol that they've most likely cracked. The mathematical algorithms that form and underlie things like AES and RSA and things like that, there are certainly vulnerabilities in those, which I've talked about, but AES 256, using GCM as the mode of operation, is an extremely secure and robust protocol that we have no known way of actually cracking. Oftentimes when the NSA or other organizations, government-sponsored organizations, have cracked security stuff, what they've actually cracked are the protocols. So as you try to put the pieces of the building blocks together, like you take a symmetric cipher and you take a digital signature and you take a hash and you take other things and you put them all together into a security protocol, the linkages, the glue that you use to glue those different things together is in fact potentially a weak link. So it's actually a problem as we build security protocols that we have to build them in ways that are extremely robust and extremely secure. It's very, very easy to create a new security protocol using very strong methods of encryption and yet create a very weak protocol. So as we think about doing that in mechanisms for assuring data provenance and assuring that scientific data sets have not been subjected to fraud, it's important that we build on good practices and well-known mechanisms for creating security protocols, and we don't create vulnerable protocols, because if we do that, we end up essentially creating a situation that's worse than a situation that we had not, if we weren't using the encryption at all. You know, if we believe that the data is correct and the data is not correct, that's a problem. If we know that we can't trust the data, and it turns out we can't trust the data, no, maybe that's not as big of a problem, okay? So it's the false sense of security issue that we need to make sure we guard against.
All right, well, thank you so much, Michael. Jim already typed in a question to the chat room. Does all of this apply to the mechanisms in key fobs that are used with cars?
I think some of it is, but the interesting thing about key fobs, I don't know exactly what mechanisms they use, and that would actually be a really interesting thing to study. But some of the issues with key fobs are in cryptography, there are certain types of vulnerabilities that are often called replay attacks. So, for example, if I send a message to to another device or to another system or to another person, and I say, you know, I want to query or I want to update, I want to send a DNS update to a DNS server, and I sign that using HMAC SHA-256. So I do it actually an HMAC on it instead of an actual true digital signature. It turns out that if I just send the same thing again, I can send the same request over and over again with the same signature, and get the server to do the same thing I want it to do over and over again. So, for example, if I send a signal to unlock a car, can I capture that signal and replay it and unlock the car at some other point? What's used more commonly is actually mechanisms for amplifying the signal that comes from a fob. So let's say you're in a restaurant and your car is parked outside. If I have an amplifier that amplifies the signal that comes from your fob, I can actually effectively use that as a replay mechanism. I can make your car think that the fob is closer than it actually is, because the fob is transmitting periodically to let the car know that it's close by, so that you don't have to push any buttons. So like on most Toyotas, for example, if you're just in proximity of the car, you can unlock the doors without actually touching your fob. So there's actually a mechanism for effectively doing a replay attack by amplifying the signal that's coming from your fob and then replaying it right next to the car. And that's how a lot of people break into cars, like, for example, Toyotas. So yeah, there are different types of vulnerabilities that are used, and I'm not sure exactly what kinds of encryption they use for all the fobs, but there are other ways of breaking into that security protocol. There are certainly ways of preventing replay attacks. I mean, very simply, one way to do it is to hash a timestamp. Okay, so as long as both sender and receiver have accurate time, or at least the same notion of time, you can actually use timestamps as a method of preventing replay attacks. But it doesn't appear, I'm not sure that car fobs actually have ways of doing that. I'm not sure. They may just have a counter that they increment, but that does not solve the amplification problem that I just described. So.
All right. Well, thank you. And Kate points out that Mazdas have about a 1 foot range, so maybe that's a little bit better than some of the Toyotas. So I had a question that I jotted down, and it was from earlier in your talk. It was mostly related to the whole idea that we need to have random numbers to make things a little bit stronger. To add in the salt, or to just assist the protocols and the mechanisms. As we get into sort of smaller and smaller chipsets and machines, there are days where I'll go, many hours, multiple days without touching a real computer, and I'm using a phone, or I'm using something smaller. And I've even convinced my parents that they no longer need a laptop; they can use something like a tablet for all their needs. As we move to smaller and smaller things, if we have sort of weak random numbers, or it takes longer to sort of decode some of these keys that we're using. You even pointed out that we're recommending 496 now, or 4096. Eventually, they're going to be recommending higher, into the 8s and the 16Ks in terms of key lengths. Is that going to cause people to get lazy as they implement some of these protocols, because the little machines can't handle the task of trying to decode all of that stuff? Is that going to force us to downgrade the security protocols so that they react faster?
Yeah, I mean, and I'll give you an example of that. There are, some of you have probably used the Cyclades or Avocent terminal servers that you can use to log into network equipment via the serial console. So these things are basically big serial multiplexers. You can log into them via SSH and then go out to a serial port and get into a serial console. Those use basically a Linux distribution. They have fairly low-end processors. And if you use a modern version of SSH as your client, it will try to use the most secure or most strongest form of Diffie-Hellman to use the key exchange. It turns out that is standard non-elliptic curve Diffie-Hellman with an 8192-bit key length. Sometimes SSH times out before it can finish doing the key negotiation on a system like that. On older Avocent boxes, it sometimes actually times out. Now, using 4096-bit Diffie-Hellman, especially if you generate the keys ephemerally, or if you generate the primes, Diffie-Hellman uses primes similar to RSA. If you generate those yourself using a really good mechanism of prime generation, and we needn't get into that. If you want to understand all of this stuff, go to the website called weakdh.org, WEAKDH, one word, .org. That explains all of this. So it's still relatively secure to use 4096-bit Diffie-Hellman primes, but if we try to go down to like 1024-bit or even lower, that makes our Cyclades Avocent boxes really fast, but it is not good for key exchange. It is actually problematic. So that's an example of how these things get slow and how there's always pressure to like reduce the keys. So again, in ESnet, what I've done is tried to to strike a balance at 4096, which is slow but doesn't actually cause operational problems by timing out when you're actually trying to SSH into a box. Other embedded devices, here's a Raspberry Pi, okay, uses an ARM processor. The Raspberry Pi has, the ARM processor actually has built into it a good random number generator, or what we think is a good random number generator. We don't know if any governments were involved in the development of this. ARM is headquartered in Britain. It's owned by a company that is Japanese that actually has several headquarters around the world. So we don't know who's been necessarily involved in the development of the random number generator in this processor, but embedded devices increasingly are getting good random number generators, and you can also plug in. You see the Raspberry Pi has a USB. You can plug in small random number generator devices, or effectively small USB-based HSMs. In fact, some of the things we use for two-factor, you can actually use as an HSM. This is a little Phaeton token here, and I can actually use that as a small random number generator HSM that I can plug into an embedded device if I need to. So what does all this mean? Well, increasingly what we're trying to do is build good random number generator into processors and into hardware. It's also getting built directly into operating systems that run on these things. So Linux and the BSDs and various forms of Unix have for many years now had very good random number generation, or what we think is very good random number generation. So my thought on all of this is phones, devices that use relatively new, good processors like ARM or small Intel like Atoms and things like that. I think those are still going to work pretty well. But older embedded devices, I think, might be highly problematic with RNGs, and that includes older CPE routers and things like that, where you may actually have issues with that. So, the moral of the story is we've gotten a lot better at random number generation, even in embedded devices, but our older devices that are still out there might have problems. We were complacent, and now we're less complacent.
All right, well, thank you. So I haven't seen any other questions fly by, so we'll just pause a minute in case anybody has any last-minute ones. Thanks again for doing this. And, I'd like to see the second part of this if you're willing to do it in a couple of weeks or a couple of months, depending on your schedule.
Yeah. So the second part, I talk more directly about DNSSEC and how DNSSEC works, and that's really a tutorial that is it was intended for ESnet staff, but I've given similar ones. This is when I'm done with it, it will be a much updated version of a tutorial that I've given at Joint Techs before and at Nanog before. So It will include some of the applications of these crypto mechanisms to DNS and DNSSEC. But it would also be useful to maybe go over some more of the applications, like how this works in things like RPKI, BGPsec, some of the other things that we use in networking. And I'd be certainly willing to do that.
Okay. Well, thanks again, Michael. And everybody who's still on, we're going to be on a 2-week pause because I have some travel and I didn't schedule anything. So look for announcements about the next one, and we'll talk to everybody soon. Have a good weekend.
Thanks.